Okay, now let's take a look at the MPI version of the character frequency solution. So just like it was with the count key problem, it's basically going to be a matter of taking the code that we looked at in the previous video and splitting it into two parts, one for the master and one for the sub-processes, and sprinkling in a little MPI communication. So here we go. Going through our program here, we have our tags for our MPI messages, just like we did before. And then we have our MPI initialization, where we get this processor's rank, the number of processors. In the master process, it'll do the sanity check on the command line arguments. It will read in the file and create the character array, just exactly like the uniprocessor version did. Okay, so that's all the same. Now this part, starting here at line 72, this is very much like the code that we had to distribute the array of numbers to subprocessors in the count key example. We have a start variable, which will tell us basically which index in the array will this chunk start at. We have our fragment size, which is n divided by 1 minus the number of processors, because that'll be how many subprocessors we have, and then 1 added to that quotient, so that my fragment size pieces are rounded up rather than rounded down in terms of their size, which means that the last fragment will always be smaller than the original or the first several fragments. Now we do have one bit that's different here in this part, and that is that since we let the user of this program supply the name of the text file as a command line parameter, we don't have a good handle on how large each subarray is going to be. Okay, so we could just make some guess and hope that the amount of memory that we allocated in the subprocessors was sufficient. But rather than doing that, what we're going to do is have one more send command for each subprocess that will tell it this is how big of an array you should allocate. Okay? So rather than sending the array and then having the subprocess gather how big it was by querying the status, like we did in the count key, in that situation, the subprocessors assumed there was some cap, and they were able to just allocate enough memory to fit in that cap by default. So here we're sending the size as a message. So the address where the fragment size is kept, one element that's an integer being sent to process I using this tag n tag, and again our communicator. And then we go ahead and send the actual array fragment. So array plus start, frag size. This is character data, and then everything else is the same. Goes to processor I, tag array this time, and the com world, and update the start location. And then the final fragment, just as we had in the count key, the final fragment might be of an odd size. So we'll figure out how big that is, send the size first, and then the array fragment itself to the last subprocessor. And then what we need to do is receive the data from the subprocessors. So to receive the data from the subprocessors, we have our counts array. It's a statically declared array here, initialized all to 0. That'll be sort of the master counts array that accumulates all the subprocessor counts. And then I'll have a second array that I need for receiving the counts from the subprocessors. I can't receive into this array because if I did, it would wipe out any previous results that I've been counting. Okay, so this one is the space where I'm going to be receiving data from the subprocessors. And note, since I'm receiving from it every time for every subprocessor, there's no need to initialize this. Okay, so then I've got my for loop goes through my number of subprocessors, executes an MPI receive using the rcounts array as the destination, 256 values it's receiving that are ints because they're counts coming from processor I, using tag counts as the tag for the communication. Once I've received that, then I can do another for loop that just goes through and accumulates the data that I received in rcounts at each index into the counts array. Okay, so after that for loop, then counts contains the counts from all the subprocesses accumulated together. So then I can go ahead and output them. So here's my for loop. This is exactly the same as it was in the uniprocessor version. Should print out exactly the same data. And then the master process would delete the overall array. Okay? All right, then in the next short video, we'll look at the subprocessor code and watch it run not only on the local machine, but also on Onyx.